We're going to look at Cunningham's anti-cycling rule for the network simplex method. We're given an uncapacitated network with digraph G. The supply values at each node is given by the entries of B, and the arc costs are given by the entries of C. X star is a feasible tree solution determined by the tree with arc set T, and we pick a node and call it the root. We say that the tree that determines X star is strongly feasible if for every arc in the tree EJ, such that the flow value on the arc is 0, EJ is directed away from the root. That means the head of EJ is not in the unique path that joins the root and the tail of EJ. So for example, if this is my root node and the path to the tail of EJ is here, we want the head to be not in the path. And if it happens that EJ looks like this, then EJ is not directed away from the root. So Cunningham proved that if in each iteration of the network simplex method, the tree is strongly feasible, then cycling cannot occur. Cunningham gave a method for maintaining a strongly feasible tree in every iteration. We're not going to see a proof of this theorem, but we're going to see the mechanics of the anti-cycling rule. So recall that this is our network simplex method, and Cunningham's anti-cycling rule only looks at this step here, step 6. So in step 6, we have to choose the leaving arc. If there's a unique R such that the flow value on the arc ER is theta, then that's the only choice for the leaving arc. Otherwise, we have a choice, and this is where Cunningham's anti-cycling rule applies. So let's consider the cycle after EK is added. Say our root is here and joins this cycle at some node, which we call J. Alright, suppose that the arcs that are candidates for the leaving arc are represented by these thick arcs. So the flow values on these arcs are theta. Another possible picture is this. So the way to pick the leaving arc is as follows. You start at the join, which is the node J, and you traverse in the direction of the entering arc. So in both pictures, we're going to traverse the cycle this way. And the first candidate for the leaving arc that you encounter will be chosen as the leaving arc. So this one here will be our leaving arc. And here, this will be our leaving arc. With this choice of the leaving arc, the new tree will still be strongly feasible. Let's see why is that. So there are two cases. Suppose that theta is positive. After step 7, the flow values on the arcs that are candidate for the leaving arc will be 0 in the updated flow. And so this arc here and this arc here will both become 0. But as you can see, after removing this arc or this arc, the remaining thick arcs will be directed away from the root. And since the flow values on the three arcs that are not in the circle are not changed, the new tree is still strongly feasible. Now let's consider the case when theta is 0. When theta is 0, after the update, the entering arc will have flow value 0. But since theta is 0, this case is not possible because this arc will not be directed away, but we assume that our tree is strongly feasible, so we must be in this situation. And in this case, the arc removed is this, and so the entering arc will be directed away because the path that joins the root node and its tail is here. And so in either case, we end up with a strongly feasible tree. One question that still needs to be answered is, how do we find an initial feasible tree solution that is determined by a strongly feasible tree?